Hello, and welcome to Control Design On-Ramp with Simulink. Control systems are everywhere, from car suspensions to self-driving vehicles, from quadcopters to commercial airplanes, and from home vacuum robots to advanced surgical robots. Simulink provides a graphical environment to create models of physical systems and to simulate their behavior. You can intuitively convert your control system block diagrams and algorithms to Simulink models. By clicking Run, you can simulate and observe the system's output. In this course, you will simulate and linearize a model of a physical system, design and tune a feedback control loop, and validate your controller against the design requirements. By the end of the course, you will build a control system in Simulink to control the motion of a robotic leg. If this looks complicated, don't worry. In this course, we will refresh you on some of the basic control concepts. It will help if you know a little bit of Simulink, though, just the basics. If you've never used Simulink before, it's easy to get started, and we recommend you first take Simulink On-Ramp to get you up to speed quickly. This course should take about 2 hours to complete, but you can leave anytime and come back later. Throughout the course, you'll be completing tasks in the Simulink editor. It's the same Simulink environment you'll encounter outside this training, but with a few added features. Enjoy the course! To start our control design journey, let's look at an example. Imagine you're flying a quadcopter drone. The quadcopter has 4 propellers. When they're spinning, they generate a lifting force and the quadcopter flies up in the air. Ultimately, we're trying to control the altitude of the quadcopter by changing the propeller's spinning speed. How the altitude depends on the propeller spinning speed, well, that's up to the quadcopter. In this example, the propeller speed is the input, the altitude is the output, and the quadcopter is called the plant. In a control system, the plant defines the relationship between the input and the output. The plant could be almost anything. It could be your car, your AC, or your vacuum robot. Let's look at the smartphone camera we saw in the previous practice. At first glance, you may think the smartphone camera is a pretty complex system, requiring you to learn optics, mechanics, and electronics to control it. Well, don't worry, that may not be the case. To get the camera in focus, all we really need to do is move the lens. When the lens moves, it changes where the image of the object falls. If the image falls right on the sensor, it's in focus, and we can get a sharp picture. But how do we know where the lens should be? Many modern smartphones are capable of measuring how far an object is from the phone camera. Based on that, the phone can do a quick calculation to tell us where the lens should go to get the object in focus. For example, if the object is 5 meters from us, the phone calculates that the lens should go to 1.72 microns. So all we need to do is move the lens to the position computed by the smartphone. The lens is driven by a small-sized motor. We can change the lens position by adjusting the current applied to the motor. Here, the current signal is the input. The position of the lens is the output, making the lens motor component our plant. Now, let's change the lens position by sending in some current signals. So far, you've simulated the plant by sending in different input signals. You may have noticed that the lens always overshoots its final position, and it always takes about 3 seconds for it to stabilize at its final position, or steady state. Ultimately, you'll design a controller to improve the overshoot and settling time performance. For classical controls, engineers use a standard set of tools to analyze the plant and design the controller. Those tools require the plant to be a linear time-invariant system, or LTI system. Time invariant indicates that the system will have exactly the same response if the same input is used, even at a different time. Now let's talk about linear and nonlinear systems. Linear means the system's output has a linear relationship with the input, while a nonlinear system's output doesn't. As you saw in simulations, the lens position difference is not proportional to the difference in current, meaning our plant is nonlinear. Don't worry, all real-life dynamic systems are nonlinear. But we can still use the analysis and design tools for LTI systems if we linearize them. Let's look at an example of a nonlinear system, a plant whose output is proportional to the square of the input. It could represent the lift force of an aircraft versus its velocity. Engineers are typically interested in the aircraft's behavior near its cruising speed. So let's draw the tangent at that point. As you can see, the responses from the nonlinear system and LTI system are pretty close near the contact point, or operating point. By linearizing the plant, you find an LTI system with similar behavior to your nonlinear system near the operating point, which means you can use the tools for LTI systems on your nonlinear system. Don't worry about the math. In Simulink, you can use the model linearizer to find the LTI system for you. To start linearization, open the Linearization Manager and select the input and output signals so Simulink can determine which blocks are your plant. Then open the Model Linearizer. In the Model Linearizer, you can specify the operating point, for example, to be the plant status after running the simulation for 8 seconds. Now, all you need to do is click a button in the Linearized gallery, and you'll find your LTI system in the Linear Analysis workspace. You can drag it to the MatLab workspace for future analysis and design. In the previous activity, you saw how you can linearize a nonlinear plant at an operating point using the model linearizer. With a single click, you obtained an LTI system and its step response plot. With Model Linearizer, you can quickly get multiple linear analysis results of the LTI system. In the step response plot, right-click on a blank area, then select Characteristics to show the available linear analysis options. For example, let's select Steady State. A data marker appears on the plot, and you can click the marker to see information about that system characteristic. Here, when a unit step input is fed into the plant, it will reach a steady state output of 0.0204. Similarly, you can check the settling time of the plant, which tells us it takes the system 18.7 seconds to settle down to its steady state. Or you can check the peak response and see that the system initially overshoots its steady state by 63.5%. The Plots and Results tab allows you to produce other plots for analysis. To do this, select your LTI system, then click on a plot. For example, the impulse response or the pole zero map. You can also use the result viewer to get the state space representation of the LTI system, or another representation, like the transfer function. In the previous lessons, we've been exploring one component of our system, the plant. We provide an input to the plant, and it gives us an output. We can then modify the input to try and get a desired output. This control strategy is called open-loop control. And as we've seen, sometimes open-loop control doesn't work very well. It can be difficult to manually find the ideal input which gives the desired output. To resolve the issue, a commonly used control strategy is closed-loop control, which is also called feedback control. A feedback control system includes another component, the controller. Chances are you've interacted with a feedback control system even if you didn't know it. Let's look at an example. You might have used cruise control on your car while driving on the highway. You change the speed by adjusting the amount of fuel going to the engine. Usually you do this by stepping on the pedal. But if you're using cruise control, this is done by the computer automatically. Here, the car speed is the output. The amount of fuel going to the engine is the input, and everything in between is the plant. The goal of cruise control is to keep the vehicle speed at a set point, for example, 70 miles per hour. The desired speed is called the reference. In feedback control, as the name suggests, the output is fed back and compared with the reference to see how far off the current speed is from the desired speed. The difference between the two is called the error. Since our current speed is less than 70, the microcomputer in the car will increase the amount of fuel going to the engine to increase the car's speed to 70 miles per hour. Here, the microcomputer is the controller. In a feedback control system, the controller takes in the error and then uses the error to adjust the input to the plant. There are a variety of controllers out there. A widely used one, and the one we'll be using, is the Proportional Integral Derivative, or PID controller. Let's look at what those terms mean. A PID controller has three elements: the proportional element, the integral element, and the derivative element. Each element is defined by a gain parameter. For example, the proportional element is defined by the proportional gain, or P gain. The error is amplified by the P gain. So, the larger the error, the harder the controller works to correct it. Similarly, the other elements are defined by the integral gain, or I gain, and the derivative gain, or D gain. In the integral element, the integral of the error is amplified by the I gain. So, the controller works harder if the system has accumulated more error. And for the derivative element, the derivative of the error is amplified by the D gain. So in other words, the controller works harder if the error is changing faster. Once we have all three, the controller adds them together, and that makes the input to the plant. In Simulink, you can use the PID controller block to quickly implement a PID controller and build a feedback control system. So let's try it out. Choosing the proportional, integral, and derivative gains for a controller is called tuning the controller. There are different methods for tuning a controller. Some engineers simply use trial and error, while others use common tuning rules or algorithms. In Simulink, the fastest way to tune gains is to use the PID Tuner app, accessible directly from the PID block. To open the app, double-click on the PID block that you wish to tune. Then, from the Block Parameters dialog, click the Tune button in the lower right. The PID Tuner app will open in a new window. If your model is nonlinear, the app will automatically linearize it. By default, the app displays the closed-loop step response of your system with the current parameters of the PID block. There are two sliders you can use to specify the design goals for your controller. The response time slider dictates the speed of the system, slower to the left and faster to the right. The transient behavior slider lets you balance another set of goals: better resistance to disturbances to the left and better reference tracking to the right. As you change your design, the values of P, I, and D are being automatically computed for you, and the tuned response plot updates in real time. This plot shows you how your system will respond with the computed gains. The original response is shown with a dashed line as a comparison. You can view the calculated values by clicking Show Parameters. This will show you both the gains and the characteristics of the controlled system. When you're satisfied with your controller, click Update Block, and the PID Tuner app will enter the controller parameters directly into your PID block. Press OK to return to your model. Then, to simulate your tuned control system, just press the Run button.